Okay, thank you very much. I think we should get started. Just to introduce myself, my name is Emma Whelan. I'm a professor of astrophysics at Maynooth University. So why are we here? We're a group of astrophysicists who've come to Mulranny to study young stars and planet formation and lots of interesting things related to this. But our conference has a very special theme. And we're celebrating the career of our colleague, Professor Tom Ray. So Tom was actually my PhD supervisor. And so as part of our conference, we decided to have this public event celebrating some of Tom's interests, and it's specifically his interest in archaeoastronomy and his recent work with the James Webb Space Telescope. So I'm your MC for tonight. And first of all, I'm going to introduce Dr. Donna Rogers-Lee from the Dublin Institute for Advanced Studies. So this conference is being organised with DIAS, with the Dublin Institute for Advanced Studies, and Tom is a senior professor there. So Donna is firstly going to tell us a little bit about DIAS.
Great, thanks a million, Emma. So, Díoghaibh agus fáilte Rove Galéir go Mála Rathní. Welcome everyone to Mulranny. On behalf of the Dublin Institute for Advanced Studies, I'm delighted to welcome you all here this evening for this very special talk as part of the Jets and Young Stars conference, as Emma mentioned. My name is Donna Rogers-Lee, and I'm a research fellow at DIAS. So I'm just going to say a few words about DIAS before handing you back to Emma. So DIAS is the Dublin Institute for Advanced Studies, and it's the world's second institute for advanced studies, modelled after the first IAS at Princeton, founded in 1940 by Eamon de Valera. So it's an independent research institute, so it's kind of like a university without the students. So we have three schools: the School of Theoretical Physics, the School of Cosmic Physics, which is where astronomy and astrophysics and geophysics live, and the School of Celtic Studies. So these may appear to be an unusual combination of subjects, but they really reflect Eamon de Valera's vision and his interests for what he wanted the institute to work towards. And so I suppose that DIAS was supposed to show the world that as the newly founded state, that Ireland was a kind of competitive place and we could really do great science. And I think obviously this conference here today really shows that today DIAS is still doing really top-notch research involving the world's biggest and best telescope. So within the astrophysics department at DIAS, we research a wide range of topics, including star formation, solar system science, including solar physics and planetary studies, high-energy astrophysics, and massive stars. DIAS also manages Dunsink Observatory, which is just on the outskirts of Dublin City, which offers open nights every second Thursday during the winter if you're ever up. And a transition year program as well, which is run for a year in case any of you know any transition year students looking for interesting things to do. We also offer final year undergraduate projects, summer internships and PhD positions. It's a very friendly place, so if you have any questions, please get in touch with us. And finally, before handing you back over to Emma, I'd just like to thank Board Fáilte and the Institute of Physics for supporting the conference and this public talk. Thank you.
That's great, thanks Donna. And of course, the location is incredibly beautiful, but it's also very interesting from an astronomy point of view because it's the first international dark sky park. So I'm very happy to welcome Georgia Macmillan from the Mayo Dark Sky Project, who's going to talk a little bit about the Dark Sky Park. And also I just want to say from my colleagues, for those of you that signed up for the trip, we're going. It's going to be a bit cloudy, but we're still going to go up. So, and Georgia we're very grateful to Georgia for taking us up. So we're going to leave from reception at 9 o'clock.
Begin.
Thank you. Is the Tom Ray in the middle? Yeah, that's it. Okay. Thank you very much, Emma, and thank you for having us. The reason we're very grateful for Emma for the invitation, and just to mark the occasion because it is so special to have this conference in the area here because of the Dark Sky Park and its connection, but to have such advanced study, literally Dublin Institute of Advanced Studies here, so we really do appreciate it. And we wanted just to set the scene, I suppose, for the context between what you're about to hear this evening with Dr. Frank Prendergast and Professor Gillian Wright, We thought that we're kind of a link between the two. So I just have a couple of slides just to put, for those that aren't familiar with the area, to put it into context of what we can see here when we don't have such a cloudy night. So this is what you could have won, perhaps. So these are some of the photos of the 10th of May. And just to point out, as Emma said, it was a Gold Tier International Dark Sky Park for the quality of night sky. And it's such an important thing for the future of people who may go into such advanced studies and astronomy and science. So thank you, Philippe. We'll just move on. The national park itself, we say half the park is after dark. Waldnathan National Park is just behind the mountain range here, up the road. We have our daytime view, Waldnathan National Park, which after dark turns into Mayo Dark Sky Park, with the view of Clagan Mountain Coastal Boardwalk, just there in Ballycraha Bay. And one of the projects that the park is working on at the moment is what we call a constellation of cottages, which is the restoration of some old homesteads that were formerly occupied, and now it's under the park land ownership. The National Parks and Wildlife have decided to restore a lot of these with the integrity of the original occupants to keep their namesakes. So we will have, rather like Scotland has the bothies and the hut-to-hut trail routes, we will have a series of 15 places where people can visit by daytime, but also, really importantly, by night, just to observe the wonder of the night sky that is so inspiring to us all. And thank you. And the connection here with our community is what really keeps this project going. The Mayo Dark Sky Park was born from a ground-up community group. And we work with Vulture Ireland, who kindly sponsor the Mayo Dark Sky Festival, with our local authority, Mayo County Council, who is so integral to our lighting policy, and of course the National Parks and Wildlife, who manage the Dark Sky Park itself. And so, just to give you a very quick context for why it's so important with light pollution, this slide here is 1997. So as you can see, as expected, the darker areas in dark green are rural and less intensely occupied. And overhead, we look at the zenith values for overhead, as you would, where you cannot see the night sky as of 1997 in the whiter and lighter areas. And Philippe, if you don't mind, just fast forwarding to 2015. Now, we are now 2024, and what's happened even almost 10 years ago is the night sky is certainly deteriorated in most places across the island of Ireland, apart from the peripheral areas on the western seaboard. But even in 2024, we don't yet have this map updated, but it is the whiter areas have really expanded across the country, and that is why it's so important, because we really try and sell the message that let's help children to name more stars in the sky than stars on the screen, and we can't do that if they cannot see the stars overhead. So that's why lighting is so important, and this is just a snapshot of some of the work, again, the community has done from the ground up with the church in Newport, where it was floodlit, causing that kind of deterioration of the night sky. We had a lighting designer give us some concept designs of how you can light without ruining the sky, but still make something integrity. The architecture kept integrity. And this is the final result, where we have a nice structure that is still lit and still visible. And then moving on to the events, and we have some of our members of our community committee here, Fiona Hopkins, and I see Declan and Carol Loftus, all local people who have put together the Mayo Dark Sky Festival.ie, I might add, which takes place on the 1st to the 3rd of November. So these are the kind of events that you can expect to enjoy. Come and join us, we hope you will. Just another slide, which is the graphic illustration of the festival. Again, multidisciplinary. We have obviously astronomy, but music, the arts, literature, all of the things that have been inspired by the night sky that are so important to us that we're trying to maintain. And we've also included the signpost there, again, from the community saying this is the beginning of the journey that we hope to link to the future with dark skies. So with that in mind, I'm going to invite Dennis Strong. We have a presentation to make to thank Professor Tom Ray for his work and to celebrate with him and to thank you all for bringing this event to Mayo. And Dennis Strong, our Divisional Director of National Parks and Wildlife, is going to make a small presentation, and I'll hand over to him now.
Thanks, Georgia. First of all, just to say, Tom, a special word of Céad Míle Fáilte to my home county of Mayo.
Yeah.
And yeah, it's a great privilege to host all your delegates here. And I think we have a lot going on in this county when it comes to dark skies. And I have to take this opportunity to really acknowledge George's work, because it's been a great privilege for me over the last 8 years to have met somebody like Georgia, and her enthusiasm for what she does is infectious, and she has educated me a lot. I'm working with the department here since 1990, and yeah, every day is an educational day when you meet somebody like Georgia and the many people who have come to experience the dark skies. So without saying any more, I'd like to make this small token of appreciation to yourself, and it's just a small token.
Thank you.
We have secured a twinning with Yosemite National Park in the US just this year. I got that over the line, and it's been a huge success. So it's our first international dark sky cooperation across the Atlantic with Yosemite, and the US ambassador, the US embassy, they chose to, we're celebrating 100 years of diplomatic relations with Ireland this year, so they highlighted in the US the twinning and the dark sky collaboration between Mayo and Yosemite as well.
Well, thank you very, very much. And I've got to say that the delegates have really, really appreciated the location. They're really enjoying it. Fortunately, the rain is holding off most of the time, which is great. And I am certainly one, for obvious reasons, who appreciates dark skies. And I'll be quite frank with you, I probably never would have got into astronomy if I hadn't experienced as a child the dark skies we had in the middle of Dublin, right? So it's very important what you're doing. Thank you very much.
Okay, so just to say thank you to Georgia. That was a great introduction, and I'd just like to thank them for all the support that they've given to our event so far. So we're going to move on to the main event, our talk on Newgrange and the James Webb Space Telescope, humanity's enduring quest to understand the universe. And as I said, this is a nod to two areas that Tom is really interested in, archaeoastronomy and then all the work that he's done with the James Webb Space Telescope. So I'm going to introduce Dr. Frank Prendergast. Frank is an Emeritus Research Fellow from the Technological University of Dublin, and he's an archaeoastronomer and yeah, an expert, so go ahead, Frank.
I do hate the label expert. It puts you into all kinds of expectations and trouble. Firstly, I'd like to acknowledge my invitation as most gracious and an honour to be here to celebrate with Tom and his family the great honour that the conference is bestowing on Tom's fabulous research. My background, very briefly, I won't delay on this, is as a geodetic surveyor by career, later academics, and my surveying took me into positional or field astronomy. So in the days of pre-GNSS, lots of theodolite work and time and azimuth measurements and stuff like that, using sun and stars. That gave me an insight into the apparent motions of the celestial bodies, and naturally I got interested in ancient history and culture and prehistoric skyscapes. And that made me migrate into archaeology, so I'm a mongrel scientist in a way, surveying, astronomy, archaeology and archaeoastronomy, so swallow all of that, and that's me. I've had the honour to be involved with Newgrange over decades, as has Tom, through the good offices of Claire Duffy, whom I'm delighted to see here today as former head of manager services, and what a facilitator Claire was in terms of any of us who ever wanted access to the National Monument and the other monuments in the area for research purposes. So that has facilitated me and Tom to get where we've got in terms of the information and results that we get out of Newgrange. So my talk is about Newgrange, and this iconic shot taken by my good colleague Ken Williams, a drone aerial, shows you the mound of Newgrange in the World Heritage Site, which is a UNESCO accredited site. And Newgrange measures 90 metres diameter, 11 metres in height, situated on the top of a ridge, overlooks the River Boyne with a spectacular panoramic view of the entire countryside and to the Dublin Mountains well to the south as well. That's the restored monument by Professor O'Kelly's work in the late 1960s and early 1970s. The mound had collapsed over millennia ago, and all of the quartz that you see fronting the monument was on the site at the foot of the mound. So he interpreted that as being likely had been a wall which studded or decorated the front of the mound at that time in prehistory. Surrounding the monument you have standing stones, which are contemporaneous now, we know, with the building of the cairn. And we're talking about 3200 BC. And it does look a little bit of artificial in terms of the restoration work, but inside it is absolutely pristine in terms of its archaeology. So that's the mound of Newgrange. It's situated between two other megatombs, Nouth and Douth, of equally gigantic proportions. But Newgrange gets all of the attention, for good or for bad, because of its astronomical alignment on the rising sun at the summer solstice. And we'll look at that in more detail shortly. It's a good point to make that to situate Newgrange in a timescale when the landscape was frozen, and after during the last maximum glacial, about 20,000 years ago, we now know that there were ice-free peaks projecting above the ice sheet. My go-to geological friends have now researched this, and scratch marks on the rock tell a tale. And when there are no scratch marks at the very summits, that tells a story that they were above the ice sheet. And if you read old geological books, you'll learn incorrectly that Ireland was totally buried under 2 kilometres of ice. The highest peak is 1038, and we now know from geological expertise that the ice sheet was about 900 metres thick across the whole of the island, and also extending offshore into the Atlantic and southwards as well. So that's all new information. So after the ice sheet, what happened? When it retreated about 20,000 years ago, and about 15,000 years ago, the climate is warming, the ice sheets are retreating, humans are then moving, and they're on the move from Western Europe, up through Britain and into Ireland, initially in the Paleolithic, and we have new information which shows that the first evidence of humans on this island predates the Mesolithic. And there's a few dates for you there. The Mesolithic was from 8,000 to 4,000. I'm still blown away by the time depth and the scale of these periods of time in terms of human prehistory. But broadly, hunter-gatherers were the people who preoccupied this landscape at that time. And in the Paleolithic and Mesolithic, you had megafauna like the giant Irish deer, Megaloceros giganteus. You also had brown bear and other creatures like Arctic fox, lemmings. They were all here, but have long since been extinct. When you move down into the bold Neolithic period, that's the one we'll focus on today, from 4,000 up to the beginning of the Bronze Age, 2,450 BC, the arrival of farming, that's the revolution. So we've gone from hunter-gathering to farming, settlement, tomb building, and the development of culture on a scale which was never been seen before. And then later into the Bronze Age and Iron Age, these don't concern us tonight. The evidence for the first humans, interestingly, came only a few years ago from the patella of a brown bear, which was re-examined in the National Museum, which had been retrieved from a cave in the 1908 in the west of Ireland. And the astute archaeologist who noticed the patella noticed these artificial or non-natural striations on the patella, made a brilliant conclusion that these could be man-made, or woman-made if you like, sent 2 samples of the bone to 2 different laboratories, and each confirmed a date of 10,800 to 10,500. That predated anything we knew up until that time. So suddenly the Mesolithic was older and we were pushing backwards. So these are just contexts for setting Newgrange in its place. Another context for setting Newgrange in its place are the housing. Incredibly, we have over 4,000 megalithic monuments on the island and countless thousands of standing stones. Yet, there are only 120 discovered foundation trenches related to houses, mostly related to infrastructural development. And if you go and visit this reconstruction of a Mesolithic or Neolithic house, it is incredibly comfortable. I would live there happily. And inside, they've got a fire burning 24/7, 365 a year. I think my earphones are dropping off just to reconnect me. Great, got it. Is that better? Yeah. Okay. Total comfort inside and a longevity they think of up to about 50 years, certainly more than a generation. That building would last. So we've only discovered the remains of about 120, subsurface, by the way, nothing on surface. So that's the style of housing in Ireland in the Neolithic. Painting a picture of life in the Neolithic, and we're getting to the astronomy eventually. I'm sure Tom Ray is saying, get on with it, Frank. But you have to understand the context of life, death, the afterlife, the patterns of life, language and population, trade and exchange. All of these things are better understood by incredible expertise in archaeology and their findings. And we have a wealth of decades of archaeological research which can explain to a limited extent what we know about the prehistoric past. But any archaeologist will tell you there is so much we don't know. And therefore, conjecture and inference fills in the gap. That's the danger. Because without the written manuals for any of this or evidence to explain how people lived precisely, we're guessing a lot of the time. And I've highlighted there cosmology because we will come to that. I'm at a conference here, I just arrived today, of astrophysics. And cosmologists in the modern era, interestingly, ask the same questions as cosmologists study, those who study ancient cosmology like me. I have a particular interest in ancient cosmology, but the questions are fundamentally the same. Man's place in the universe. Where have you come from? Where are we going to? What is out there and what is up there? And that was not understood in prehistory. And to a large extent, I think, although the boundaries have shifted, there's an awful lot we don't know. That's why you're here, I guess. But that kind of summarizes the questions that are raised by life in the Neolithic. And what you see there is the inside of a burial chamber, inscribed with megalithic art. Ireland was obviously a hub of cultural expertise in this area and richness. Ireland has 80% of all megalithic art in northwestern Europe. So something special is going on in Ireland in relation to the sophistication and the engraving of stones in particular. And much thought and argument goes into the meaning of these symbols. That's an endless point for discussion. Here's a laser scan cutaway supplied by my good colleagues in the Discovery Programme, Centre for Archaeology and Innovation. And there what you have is a 3D model produced by laser scanning. So you're talking about sub-centimetre resolution in terms of accuracy. But what you see there is the burial chamber, if I can get the, yep, here, and 6 meters in height, ascending in gradient from the entrance as you go into the tomb, and you have the special entrance area here, studded with boulders of quartz and granite collected at some distance from the site. In one instance, the quartz which studs the facade is collected probably 80 kilometers from the Dublin mountains. So that's one hell of a journey. So that's a side view and a slice through the mound at Newgrange, which is our focus. The entrance is especially special because as you walk up to the main entrance, above you is a lintel stone, which is RS1 on your slide. And above that again, there is a decorated roof box lintel, the one which is highlighted there, and I've used artistic license borrowed from Claire O'Kelly, an archaeologist who drew it, because a lot of that decoration is quite faint due to weathering. And you can see there that something special is going on in terms of Newgrange. It has a slot opening. There's a metal bar, by the way, running across, which has to be there for stability reasons. And the dimensions are quite small. They are polygonal rather than rectangular. And they vary from 15 centimetres, I notice, 15 centimetres to 28 centimetres, and nearly a metre across. That's looking into the tomb, and it's through that opening, the roof box opening, that Professor O'Kelly discovered in the late 1960s something rather special, that sun could penetrate around the period of winter solstice sunrise directly into the chamber. And if I go inside and take the out view, and we have a laser scan to guide you or walk you into the chamber, you have the side orthostats, which line the tomb itself, the entrance passageway, and you're rising over a metre in gradient. And mercifully, the whole thing is still intact 5,000 years later, into a magnificent burial chamber, 6 metres high, exhibiting something very special, cruciform side recesses, almost uniquely Irish in terms of architecture, with basin stones for the deposits of the funerary remains of the dead and bones of adults and sometimes young children. And you can see the structure in all its glory, and you can still visit. And Newgrange is a great admirer of your €10 note, so do go and visit. And there's the corbel ceiling, right up to the top with a capstone, totally waterproof, and the reverse side or the outsides of those inclined stones are channeled to actually take rainwater away out of the chamber. So the first bit of weatherproofing, I would guess, in Irish prehistory. Taking the out view, what I've done here is I've mapped onto the roof box the sky, and I've mapped it for 3200 and also for AD 2020. And you can see that there's a shift between sunrise now and sunrise then, all due to the obliquity of the ecliptic, or in layman's terms, the tilt of the Earth's axis changes by about 1/2 degree. That produces a little over 1 degree in azimuth or direction, enough to make a difference. And my own work, because Tom has done a lot of work at Newgrange as well, shows that as this obliquity cycle continues, there's a problem at Newgrange, because on the left you will see that the rising sun is coming out of the left side of the roof box as we look at sunrise. So millennium on millennium, as that cycle continues, we're going to lose light in Newgrange. So the value of capturing the phenomena in a research project, which I'll describe now, can't be underestimated. Now if you watch the top, present day sunrise, watch the bottom, 5,000 years ago, and the effect of obliquity is obvious. There's another phenomenon on the horizon. Do you know this distinctive forest or tree growth? It would have been comparatively easy in prehistory for anyone aware of the sun's movement or apparent movement on the horizon to note the position of the sun at the winter solstice, referencing memorized distinctive features. So the actual task of figuring out where the sun will rise, not difficult at all. What is difficult is the challenge of constructing Newgrange in a special way that facilitated the light going into the chamber. That was the engineering genius of the time. There are 220 extant passage tombs across the island, of which about 23, the red dots on the left, can be argued as being passage tombs which have solstitial importance in terms of sunrise or sunset. And you can see that the bias is on the top half of the island, and that's where most of the tombs are. Statistically, we all like to examine probabilities, and there are now advanced softwares to look at this. And the bad news is that if you take pure statistics and probability and apply it to all of the orientations which I've measured through fieldwork, you get a disappointing answer. There is no strong indication of intentionality across all of them, taken as a group. But when you break it down then into individual tunes, there's different things going on which I can't talk about tonight due to time. But if we look at the result of the project that we have undertaken, it was Claire Tuffy and her genius during the pandemic, when the monument was closed to the public, actually phoned me and said, "Frank, can we do anything useful during the closure?" And we had a discussion and a chat, and out of that came incredible support from government, the various agencies. A team was put together to see could we broadcast the phenomenon to the world. And that's what was done. And boy, was that a mega success, because at a time of global depression, this thing, I still get emotional about it, because we were there, Claire and myself, presenting to the world, and that was just something else. But we did the project, and the results are briefly as follows. On the left, you see a simulation which I've recreated, and it was Tom Ray's work, pioneering work in the chamber some years ago, which did a precision survey and figured out that in the Neolithic, the sunbeam into the chamber would reach the end recess, the backstone you can see on the left. And that was new work, and it was groundbreaking work, and so important. And on the right, we have a pictorial view of what is happening now. Obliquity has changed things. Also, the inward leaning of those big stones in the passage has minimized the amount of light that can go into the chamber. Nonetheless, it works. It still works. What I'll do is show you some examples, but on the right, you have a time-stamped image taken by an aerial or vertically pointing downwards camera, and we had a battery of cameras and video cameras in the chamber recording everything precisely timed. And along with the geospatial work that I was doing, we were able to produce orientated, exact maps of the phenomena over many, many days. And the first view ever, I believe, of sunrise taken from the roof box lintel stone shows you just on the outside what was happening on the horizon. And if you take the inverse or reverse view, you have that beam of light pushing through, uninterrupted, into the floor of the burial chamber at the back. And that was, I believe, a first ever in terms of that kind of image. And of course, we had official permission to do it, because the government were funding it. So that was nice. And if you look at this quickly put together compilation of digital stills, you get speeded up what is 20 minutes of duration in real time. So never before has this been captured with this kind of resolution. And I compliment the expertise of the National Monuments and the photographer John Lawler especially, and it was his skill with the camera, monitoring the aperture changes constantly. And this was broadcast out to the world through technologies and outside broadcast units. So it's a 20-minute long phenomenon and occurs over a period of a few days, but in fact we discovered a lot more in terms of the duration of the number of days when light enters the chamber. So to finish off, the experience of viewing the light at Newgrange, as Claire Tuffy put it famously, waiting for the light, is a numinous phenomenon by battery. It is sacred, and must have been sacred in prehistoric Neolithic Ireland, because the function of these monuments was funerary, and it was also ritualizing something special at the turning point of the year, when the shortest days of the year are there. The sun has moved as far south on the horizon as it can go. It starts to reverse. And that phenomenon of winter solstice sunlight and marking it is something that happens throughout many cultures globally, not just in the Boyne Valley. And that's my talk, and thank you for listening.
that wonderful talk. We have a few minutes if anybody would like to ask Frank a question, and then we can take some more questions at the end. So do we have any questions?
Which you have, Matty.
I'm asking Frank.
Yeah.
Yeah, might be easier with that. Thanks. Yes.
Frank, when the tomb was worked on way back, did they move the stones in the main passage, and obviously then were they replaced obviously very accurately, and
No,
or were they left as they were?
Within the entrance passage, all the way up to the chamber, nothing was moved or could be moved because structurally you wouldn't dare. Such is the potential instability of the whole thing. But the entrance area had a lot of restoration work done, and my colleague Ken Williams has done a forensic-like re-examination of Professor O'Kelly's archaeological drawings, and meticulous care was taken with any of the dismantled stones around the roof box area to ensure that they were reinstated as they were found. So that was essential work. So I think we can safely say that what you get now in terms of the in situ stones is as they were in prehistory.
Thank you.
One more? Yeah, thanks.
Usually the questions get harder and harder.
No, easier. I was interested in the Ice Age.
Yes.
The picture that you showed earlier. So how is this, where was the picture taken? Is it here? Or
No, that's just a generic picture. But based on my conversations with Irish geologists, the information I've given you in terms of the absolute height of the ice sheet as being a maximum of about 900 metres thick is correct. And that's based on geological examinations of these nunataks. And for anybody who doesn't know the word...
Nunatak, that was my other question.
Yeah, sorry?
What was that, a nunatak?
A nunatak is an Inuit word borrowed by geologists, and what it describes are ice-free peaks above the ice sheet. And it's a very good word, actually, and I think translated would mean no ice.
Okay.
No ice, nunatak. And no scratches on the on the peaks that rise above the ice. And that's the clue to the absolute thickness and depth of the ice sheet.
And how do they determine the timing?
The timing I'm not too sure about, because that would be, as they say, not an ecumenical matter but a geotechnical matter. That's not my field. But actually, I mentioned, just to diverse, I mentioned scratch marks. I didn't mention that the entrance roof box was discovered on excavation to have one quartz block in situ inserted into the opening. Beside it, they discovered scratch marks on the lower and the upper surfaces of the lintel, suggesting, and probably reasonably so, that the quartz blocks, which is a hugely symbolic stone, by the way, were inserted and extracted periodically, hence creating the scratches, to control light and dark ritually and ceremoniously and periodically. And I think that's a fair conclusion in terms of what was going on at Newgrange. So for most of the year, it was probably sealed up in terms of maintaining total darkness inside. And by the way, at the outside of the tomb, there is a big orthostat which was found adjacent to the entrance and moved. When they repositioned it, it fitted perfectly into the entrance. So it functioned as a door stone. So the entrance to the tomb was sealed by this enormous weight of a door stone, and then the roof box above the lintel sealed by quartz blocks. Interestingly, in the Irish language, the name for quartz is Clochnagrania, or sunstone. So that actually comes down the generations in terms of an interesting link. So quartz is a very special stone and used extensively at Newgrange in a variety of contexts.
Thank you.
Okay.
So
Yep.
we have one more question, and then maybe we can
Sure.
take more questions at
Yep.
the end after Gillian's talk.
Thanks very much. A friend of mine, Anthony Murphy, you know him, he discovered the Dronehenge.
Yep.
Is there any plans to kind of, to do any excavation work or archaeological studies around that, or is it going to be something way down the line?
I think it's something way, way down the line, insofar as the last drought, I think it was 2018, was such a severe drought here and in Britain that enormous discoveries were made across the landscape through crop marks. And that is basically subsurface patterns due to the drying out, differential drying out of the soils due to drought. And they revealed in Britain and Ireland extensive structures which were ceremonial in many cases, very large structures, circular very often, concentric circles, set out with great regularity and accuracy probably, and ritually used. There are so many of them, they are recorded, and that's as far as we go. The costs of doing a major excavation, even if you take the Boyne Valley, Newgrange is in the middle of two tombs. The one to the right, if you look to the river, is Nouth. That has been completely excavated over 20, 30 years by George Ogan and produced 7 volumes of archaeological books just on that one. The other one, the sister of the third one, Douth, has never been excavated and may never be at the moment anyway. These are enormous projects and there are so many of them. And I said 220 passage tombs across the landscape. Many of them are just in state ownership and caretaking. And that's all you can do with most of them, look after them. So that's, I think, the answer.
So with that, I think we should thank Frank. Thank you. Okay, so we're going to jump forward more than 5,000 years to the 25th of December 2021 when astrophysicists across the world got the best Christmas present ever with the successful launch of the James Webb Space Telescope. And I'm really very happy that we have Professor Gillian Wright. Professor Wright is the director of the UK Astronomy and Technology Centre in Edinburgh, and she is the European Principal Investigator of MIRI, which is the mid-infrared telescope or instrument on the James Webb Space Telescope. So hand over to Gillian, thank you.
Hi, and I'm really honoured to have been invited to talk here and to recognise Tom's long career and his long involvement with this mission, with my talk. So what I'm going to do is a really, a really whirlwind tour through, it's an infrared mission, what is infrared astronomy, a bit about the mission and the telescope that I hope will give you an idea of what was involved in building it, and then something about how we're revealing new things about the universe to finish up with. So, is that the wrong way?
Yes.
Or it's not talking? No, it's on. It was the wrong way. Right. Okay, so infrared light is the light, I think of it as the light that is beyond the red. So you can see the little rainbow, that's the visible light our eyes are accustomed to. The infrared is all of this red stuff, and that's what James Webb has been designed to look at. And if you look in the infrared, you see things differently. So I've got some pictures to illustrate that. This is a colleague of mine. In this picture, things that are coloured white and red are the warmest, and the blue is the coldest, so his tie is very cold because it's not really attached to his body, and his eyes look cold because my friend wears spectacles. So you can't see the warmth from his eyes. Alternatively, here's a picture of a cat. Cats have got a nice fur coat, so you can't see much of their warmth, and we perceive infrared radiation mostly as warmth. You can see its eyes, and in another illustration, and this is some of what astronomers are really interested in, is if you look in the infrared, you can see things that you can't see in the visible. So this is a picture of a carpet, and this is what it looks like in the infrared because somebody walked on it and warmed it up a little bit. So we want to look at the sky at infrared wavelengths, and that's a difficult thing to do from the ground. And the reason it's difficult to do from the ground is because our Earth's atmosphere is not only very good at protecting us all by absorbing UV light, it's very good at absorbing infrared light. So you can see again the rainbow that our eyes can see. We have large ground-based telescopes. Mostly they work at optical wavelengths, and they can see just little bits of the infrared, enough to give us tantalizing glimpses of how wonderful it would be if we could have a big telescope in the infrared for our science. On the other hand, in space. It's very difficult to put things into space, and so mostly what we've had is small space telescopes, and they've also told us that looking at the universe with infrared eyes, if you like, is a really interesting thing to do. We can learn lots of new things about galaxies and stars and planets. So the idea of a large infrared telescope in space has been kind of like a dream for a long time for lots of people. And that's what JWST is. It is the biggest telescope by a long way ever launched into space. And to do this, because it's so big, it doesn't fit in a rocket as a telescope. So it had to be all folded up to fit into the rocket. And then we wanted to look with infrared eyes. And I just explained that we perceive infrared radiation as heat. Well, unfortunately, so do detectors. Detectors can be warm. The detector in your mobile phone is warm intrinsically. So we had to make it cold so that we could see this faint heat radiation coming from the universe. And as we already talked about, it was launched as a nice big Christmas present, at least for people like me and Tom, I think, on December, Christmas Day in 2021. So it's many, many years developing this. It's been a really big, ambitious project. These sunshades that you can see in the pink here, they're the size of a tennis court. They are huge, and they are made of an incredibly thin material. I can show you some more pictures of them. And they're vital, because being able to shade the telescope and cool it with this sunshade is the technology that makes it cold so that it's sensitive at infrared wavelengths. So I said it took a long time, about 30 years. I don't know how long it took to build Newgrange, but 30 years felt like a huge amount of time. And it's generational. So there were people helping us at the end of this project who were part of the MIRI team who were not born when some of us started. So it's a massive effort to do this. Started in the 1990s with studies by NASA, and then ESA and the Canadian Space Agency joined the project in 1998. I started working on it shortly before that, along with a number of colleagues in this room, when we were thinking about what could Europe potentially contribute to the mission, and also doing design studies. And then once it becomes formal like that, it changes from, oh well, what could we build, and do you think we could make a telescope like that work, and what kind of science might it do, to, okay, so this is the thing we're going to design and build. It was another 6 years after that before anybody actually started making anything, and mirrors are always some of the first things you make for telescopes. So in 2004 we started making mirrors. There was still a debate going on about how it was actually going to get into space. And then, you know, the mirrors were completed. The mid-infrared instrument, which is the thing I was involved with, we delivered that in 2012. And then it took 4 years to build that into the telescope, and then skipping ahead, lots of years of testing to make sure it would work, and developing software. It was eventually launched. So it's been a very long development. There have been a lot of technical challenges, and I just thought I would highlight a few. One is, you can see, let's think, where's the pointer? Which thing lights the pointer up on this? This one? Yes, there we go. So this is the sunshade in construction. You can see, here's another picture of it, so you can see how thin and not nicely. So think about cling film. When you look at this, I always think about cling film. Not because you would ever make a tennis court size layer of cling film, but because it's a good description of how easy it is to tear and how frustrating it is to try and fold it. And that's a problem that the engineers had to solve. You can see it here. This doesn't look like a telescope. This is the JWST telescope, all folded up just prior to being moved into the launch vehicle. You can see the mirrors in pieces. This stuff is all folded up in here. And then when it gets into space, it's all going to have to unfold. So that was a massive challenge. And where did it go? So, and where is it now? So it's in a place that we call L2, which is a kind of a neat point, where the gravity in our solar system helps it to stay there. And unlike other missions and the satellites that provide our communications, JWST is not going around the Earth, it is going around the Sun with the Earth. So it's out here, 4 times further away from the Earth than the Moon, and then JWST and the Earth are going around the Sun together, and that means that beautiful sunshade is always pointed towards the Sun, and at the same time, over the course of a year, we astronomers get to be able to observe the whole sky with JWST if we want to. So I mentioned the mid-infrared instrument MIRI. So if you think about telescopes and instruments, think about a camera, you know, the kind of camera with a big zoom lens on it that professional photographers use. So the telescope is the equivalent of that big zoom lens. It's a ginormous zoom lens for zooming in on the universe, and that's what it does beautifully well. The instruments, on the other hand, are the rest of the camera, the body of the camera, where the optics are, where the sensors are that actually take the pictures and record the data. So the instruments are a really important part of this system, and the mid-infrared instrument is special because it's the only one on JWST that can look at these mid-infrared wavelengths, and this was the thing that we all got involved with in Europe, and we built an international collaboration amongst a number of countries and institutes in Europe. I think in the end we had 27 different institutes contributing from all across Europe, along with partners in the USA. So this was a big international collaborative human effort to build something like MIRI. And since we are talking about it, and it's the only one, being ambitious astronomers, we get one chance at this, so we packed everything in the sort of modern astronomer's toolkit for looking at the universe at mid-infrared instruments into this instrument. So we can take pictures, we can make what we call spectra, so we can split, instead of having a rainbow, whoops, went the wrong way, right. Instead of having a rainbow of optical that we can see, we can make effectively a rainbow of the infrared colours and split the light out and look at each different component of that. And we have coronagraphs, which can be used to block out the light from stars so that we can see the planets that are going around them better. And this is really important to acknowledge. This wouldn't work without the things that Tom and his team contributed. So one of those was we had an Irish-Swedish collaboration to provide all the filters. If you want to take pictures in red light or green light, you know, you would use a filter with your camera. MIRI does exactly the same thing. We have filters, and in the spectrograph we have special filters called dichroics that split the light for the spectrograph and help to split it out. And those were led by Tom's team here and a team in Sweden in a collaboration to provide them. The instrument can't do science without them. So that's a key contribution. But the other thing that the team contributed over all these years is some of the software that's so vital to timing something that is measured. So when our data comes from the telescope, our spectra look something like this, okay? And buried in that digital signal is this. It's a beautiful spectrum or an image, and so there's a lot of software involved in going from this to this, understanding, modelling the instrument, and then writing the software to do it. And Tom's team here played a key part, along with all the collaborators, in developing that system as well, and in testing the instrument. So this was about the last picture of MIRI. You can see it's all wrapped up in its thermal shield, because one of the real challenges of the MIRI instrument was it had to be even colder than the rest of JWST. So it is cooled to minus 266 degrees. That is only 7 degrees warmer than the temperature at which everything in the universe would stop. So you're warm because all the atoms in your body are vibrating. All of that would just stop at 0. So we're just that little, and that's us 35 degrees colder than all the rest of the mission. So that's a very difficult thing to do, and that's where our colleagues in the US provided us with a special fridge, which you can see part of up here. So this is the MIRI instrument. It's all wrapped up in these blankets to keep it cold, and this is our own special dedicated fridge to make us even colder than the rest of the mission. So I'm going to skip ahead and say, after all that testing and the software writing, we launched on Christmas Day, and that was very nerve-wracking, but it was a perfect launch. And because it's a perfect launch, we've got a much longer mission now to do science. So that was a wonderful Christmas present for astronomy. And one of the things you have to do then is, you think about it, a launch is just a controlled explosion in a rocket. And it's not very controlled, so the rocket is shaken, and our instrument and the whole telescope is shaken by 80 times the force of gravity. So when you do that, all of those mirrors in that telescope that had to be made in little segments and then folded up, they're not in the right place anymore. So you have to work out how to put them into the right place. And you start out by finding which mirrors are which, so you get images from each mirror. And then you have to slightly bend the mirrors to make those images perfect. And then you have to tilt them to bring them together so that the whole mirror of the telescope acts like one great big optic. And so what you look at when this is done is then the sharpest infrared image of a star that's ever been made. And once we have that, we can go on and do some science. So I said this was, JWST was like a ginormous zoom lens. So this is comparing our best ever mid-infrared image, and then we're zooming in on it like you would with JWST, and you can see it's completely different now that we have a big telescope in space in terms of the detail that you can see and the wonderful structures that we can now go and study. So this is the old compared to what we can do now with the new mission. And before I talk, I'll show you a little bit of some of the science that's coming from the mission, and that we're all here this week. Some of the discussions this week have also been using data from JWST and from MIRI. I can't emphasize how much this is a human endeavor. People made this, people do it, so there were more than 20,000 scientists and engineers involved in the construction. It went over 30 years or thereabouts. If you look closely at these pictures, you can find Tom in many of them. He might even remember some of them. Yeah, he says. So I think you know, it has been a fantastic collaboration. It's a real privilege to work with other people like this. It can be difficult, can be a lot of fun, and I think, you know, everybody contributed, everybody played their own part in making this mission happen. So one of the things we are finding is lots of galaxies. So this is a near-infrared JWST image, and you can see that it is full of little dots. All of those little dots are galaxies, and some of them are galaxies we didn't know were there, because the galaxies are so red that you couldn't see them in the optical. So you can see lots of little red. So there are some of these red things, at the moment they're called little red dots, because they are so red, and they're not very little really, because the other thing we are finding is that there are more of these red galaxies than we thought there might be, and on the whole they've been busy making more stars than we thought they would be, and some of them have been making black holes, and there are more black holes in the early universe than we thought. So there's lots of things now that we can take these images that we're learning about the universe that we just didn't know before, and we don't, so we can kind of say our current theories, they're quite good, but they don't stretch quite as far as being able to explain everything in this image. So we're really into discovery space now, discovering new things about the distant universe. But we're here to talk about jets and beyond, which are associated with a different question, which is about how are stars and planets made and what happens when they're making. So I think there are other people in this room that can probably explain this to you much better than I can, but I'm going to have a go, right? So you start with a dense cloud of gas, and that gas starts to fall in on itself. Under its own gravity, it's collapsing. And as it collapses, the middle gets denser and denser. And so now you have something heavy in the middle here, and it's going to attract other things. So it starts to build into a protostar and to rotate, and you create disks from the rotation. And within those disks, that's how planets form, and eventually you end up with something like our solar system. So all the detailed steps along this process, we've got quite a good understanding. And then, well, so this conference is called Jets and Beyond, and somewhere in this process, some of these protostars, baby stars in the making baby planetary systems, some of them start making jets. And to be able to understand the physics of those jets and what's happening and try and tie it all together is one of the big interesting questions in current astronomy that we're being able to start to tackle. So let's go. And a different type, and a related question about this is, for example, where did the water on the Earth come from? Where did it come from? Then there's different models that would explain that. In one of them, the water was already in that disk when it formed, and it stayed there, and it kind of got on the planet. And in another model, the water, it got too hot, and the water all evaporated, and then the water had to come back from somewhere else. Both of those fit our current data. And so a different way of answering that question is maybe to go try and look at a different system and see how that compares to what we know about our solar system. So this is an example, again, back. So in this example, we're looking in this planet-forming region of the disk, and we have detected water. So in this system, the water was there, and you can see, the way you can see the water is, this is what we call a spectrum. So the black line is the thing that we measured, and the blue is what the chemists tell us the water would look like. And you can see it's an almost perfect match. So we're pretty confident that this is water having been found. And so this is new ways of addressing even questions like, where did the water on Earth come from? By studying other systems and being able to look at them in detail. And jets, I mentioned jets. Well, this jet has been known about from those, I remember I said there was big ground-based telescopes trying to do infrared science and the small missions. It's kind of very interesting because it's almost perfectly aligned. So if you have jets coming out from something, sometimes they're going to be just firing at you, and so you don't get to see the entire. So one of the things that has been happening is you can see this. So here's this protostar, you can't see it, it's in here, and this is all the material that is being thrown out in a jet. And Tom and his team have been able to even map how this material is moving over the ages. So now we can start to understand a lot about these jets, and because MIRI also has the ability to do spectroscopy, we can start to say, well, what's in the jet? What's it made of? What are the elements? A lot of it, the answer is a lot of it is molecular hydrogen, but that molecular hydrogen is being shocked by being thrown out, so it's at different temperatures, and you can start to understand something about chemistry and dynamics in these systems. And then in the future, that will help to refine our understanding of how planets form around stars and how stars form. So what I would like to do now, if it works, is ask you to just sit back and enjoy how beautiful the universe is when it is looked at in detail like this with JWST, and to say thank you very much for listening to me, but please enjoy the images. these are all just from the first year with the telescope. So.
Thank you very much, Gillian. That was really wonderful. Questions?
Yeah.
Yes. So, anyone want to ask? Any questions?
No, that's good.
Yep.
What's the oldest object that the telescope has managed to visualize or detect?
Whoa. Ah, that's quite a hard one. About 13 billion years ago.
So right on the edge.
Yeah.
Yeah. That's the great thing about JWST. It can really show you those galaxies right on the edge.
Yeah.
Because they're so red, otherwise we wouldn't be able to see them. Any other questions? Yes, yeah. Frank.
Gillian, fantastic talk. Testimony to the brilliant engineering that went into this, but it is so far out it can't be repaired. What are the plans if anything goes wrong?
Live with it as best we can.
Yeah.
So some things there are redundancies. So you know, for example, the system that keeps it pointing in the right places on the sky, that could be switched to a backup system. But for other things, it would be a question of just trying to figure out how to work with it the way it is.
There's a question way back. Maybe there's a mic.
How long will it be able to function?
We're expecting 20 years, plus or minus nothing going wrong, as Frank just mentioned.
Excuse me, there's another telescope plan.
Not so there are some early discussions going on about potentially another very large telescope. It's called the Habitable Worlds Observatory. It's in the very, I wouldn't say it's yet at the stage of being planned. It's more at the discussion, at the what might it be discussion stage.
Oh, I read that for something like 30 years.
Yeah.
And the universe is expanding.
It is, yes.
The closest star to us is something like 4.2 light years away, is that correct?
Yeah, that's about right, yeah.
Yeah, these are billions of light years away. Some of the can't be
Yeah.
Yes?
Has the telescope has it ever discovered any new black holes, or?
It's discovered lots of baby black holes in the early universe that we didn't know about before.
Sorry, for a non-expert, what is a black hole?
A black hole is something that has so much gravity that no light or material can ever get out of it.
Okay, thank you. And another question, how much has all of this cost? I mean, it's amazing for somebody who knew nothing about astrophysics and just heard about it today. I'm blown away with this evening's information. Absolutely illuminating, thank you. But one, how much has it cost so far, and what's going to cost to maintain? And where's the funding? I see we have NASA, ESA, we have our own Enterprise Ireland giving some funding, but is funding guaranteed, or is that a never-ending job trying to source new funding?
So,
hardest question of the night.
Can I add something?
Yeah.
If we stop the wars, if we gave people enough to eat and didn't try to satisfy the rich so much, maybe we'd have unlimited money.
There's different ways of answering your question. So one way that the project manager at the European Space Agency describes the cost in Europe of participating in the mission is that it's the cost of a cup of coffee once for every taxpayer over that 30-year period.
Right, good value.
Yeah.
And it's one very cheap cup. It's not your Starbucks coffee, it's about €2 coffee.
So the cost that NASA quote in total, which includes their expected cost of operating it, so it includes
20 years of operation.
Probably the first 10 or something like that, and then you look at it again. That's $10 billion. Nearly all of that cost is in people. It's paying the salaries of the scientists and the engineers for 30 years to work on designing it and building it. And that's the ongoing cost. The ongoing cost is the cost of the people at the Space Telescope Science Institute that are making sure the data comes down and that we can all do our science with it.
Thank you.
Is it very difficult to have to fix your technology at, say, the certain year? I can't say you said it was 2004, and then you have to lock it off, and then you see all these massive developments years as the years go by. If you were to design it starting today, would it be very different?
It would be somewhat different because you learn things by having designed it and built it, and so you take that learning into the next thing that you build. But in other ways, there isn't some magic new technology that would make this 10 times better than it would. This actually created the technologies, it pushed the technologies to as far as we possibly could. So it's kind of, I'm giving you another yes and no answer, aren't I?
A huge relief, I'm sure. As in, there could have been a revolution 3 years down the line where you go, oh, we have to start.
And there wasn't things like that. And some things, for example, the detectors that actually do the measurements, they're absolutely state of the art. The companies that make them at the moment can't actually make better ones, but there are some people at DIAS that are studying how to make a completely new type of detector. So there's a poster about it up over there, in fact.
Do you do these kinds of talks in any schools in Ireland? Because I kind of figured that you could get into people when they're young.
Yeah,
and maybe that would give them enthusiasm, stimulation.
Yeah, I mean, maybe I can speak, a huge amount of the work we all do is public outreach. As I said, Tom is a professor at the Dublin Institute for Advanced Studies, and they do a lot of outreach. They have done Sync Observatory in Dublin, and they have public nights very, very regularly. So.
Yeah, I mean, there's a lot around the country promoting astronomy, and it's very important. I'm sure it's the same in Scotland as well, in terms of stimulating kids go in to study science and engineering, and it's very, very important that that's promoted.
It would be great to get the local national school. We have a national school in Mulranny, and maybe there's some follow-up material from tonight, because as I said, I didn't know very much and I found it all easy enough to understand.
Yeah.
But as a follow-up to the Mulranny National School, because of the proximity to the dark skies and having all these experts here in Mulranny for 3 or 4 days, I mean, it's incredible.
And there's a connection to the dark skies.
Yeah.
Okay, we can all look up at the sky and see the stars and ask questions about what we're seeing and how it would be. And that's exactly the process the scientists use when we use our telescopes to do it. It is so it's relatable in that sense. I think every country that participated in the mid-infrared instrument, we've all got programs in our own countries about going into schools, telling people not just about the science, but about the teamwork that it takes to make it, and the fact that you need every range of skills to do something like this. It's not about some smart scientist saying, oh, I know how planets form. It's about building the tools to understand it.
And maybe I can say that we did contact all of the local schools to tell them about the event tonight, and the event is being recorded and it's going to be available online for people to watch.
Yeah, well, I'd be happy to put that out there. Thank you.
Okay, so I think.
Oh, one more.
One more question. That's your second question. You're privileged.
How far can the James Webb Space Telescope look out to?
In distance. Now, I'm not sure I can calculate that into distance.
How far can the James Webb Space Telescope look out to?
Okay, I think I can answer that. So it was said that the nearest star to us is 4 light years away. Okay, 4 light years. What that means is light travels at 3. Okay, you know. Maybe some of the others don't. Thank you for putting me in my place. So there's light travels at 300,000 kilometers a second, right? So in 1 year, you can imagine how far light can travel. So the most distant objects that JWST are looking at are about 30.4
billion years away. Yeah.
A long, long time ago. Because you're looking back and back in time. And
looking back.
Not near enough. Getting closer. Okay, I think on that positive note of how big the universe is, can we please thank Gillian